All right, so what I'm going to do today is just do a quick recap of what we did yesterday with graphing polynomials and add a little bit more that will help you go moving forward. So we think about general shapes, polynomials. We talked about if we're talking about so when I say even degree, positive leading coefficient, like a 4x to the 8th. We're talking about the end behavior. At the ends, both arrows are going to be going up. If my degree is even and the leading coefficient is negative, at the ends, like a negative 7x to the 100, at the ends, they're going to be going down. In the middle, anything can happen, like whatever, okay? But we're talking about the ends. So odd degree, positive leading coefficient. That would be something like 4x to the 7th. We know that the arrows are going to be in opposite direction, rising to the right, falling to the left. I call that a positive John Travolta. Odd degree, negative leading coefficient, like a negative 4x to the 9th. Opposite directions, falling to the right, rising to the left. Okay, so those are our general shapes. We think of the degree leading coefficient. Now, when it was in factored form, this is what we did. We found the zeros, we list the multiplicity. Even multiplicity bounces. Odd multiplicity crosses. Find the degree. Even degree, it's either got to go up and up or down and down. Odd degree, positive John Travolta, negative John Travolta. Okay, so but that's in factored form. So that's really where right-hand rule, this is when it's a negative leading coefficient, positive leading coefficient, positive leading coefficient, negative leading coefficient. Okay, so we think of, zeros, intercepts, factors, solutions, all those things are the same. They're just different names for the same thing. Okay, so standard form of a polynomial would be something like f of x equals 8x to the 7th minus 9x to the 6th plus 7x squared minus 2. I could not ask you to graph that. Only thing I could ask you to do is tell me the end behavior. All this stuff we don't care about. We care about this. 8x to the 7th. Positive, odd. What do I know about a positive leading coefficient and an odd degree? It's a John Travolta. Now, if it's factored form, something like f of x, which is what we did yesterday, x minus 2 cubed, x plus 5, x minus 1 squared, I can ask you to actually graph that. So that's when we found our zeros. X equals, so you're paying no attention to the power. You're just putting your zeros. X equals 2, x equals negative 5, x equals 1. Look at the degree, okay, which is the multiplicity. Odd degree crosses. Odd degree crosses. Even degree bounces. So I know I have a dot at 1, a dot at 2, and a dot at -5. But how are my arrows going at the end? I need the degree of the whole thing. I do that by adding up the multiplicity. So I would have 3 plus 1 plus 2, which is 6. Even degree, up and up or down and down. I look at what's in front, it's positive, so I know this has to go up and up. Now, I got to think about the crossing. Well, it crosses at -5, so that means it's going through it, and it's going to come hit at 1. Well, it bounces at 1, so that means it doesn't cross through. It bounces, comes back down, then goes through. It's a generic looking graph, but that's how you do it. The only way factored form could be different, like where I could ask you, if I asked you x cubed plus 7x squared minus 8x, I could ask you to do that because you can factor that. That's where we need to remember, how do I factor that? Greatest common factor. Then I'd have x squared plus 7x minus 8. I can factor this. That would be x plus 8, x minus 1. I can graph that. That's 0, that's -8, that's 1. So my zeros are 0, -8, +1. They all have multiplicity of 1. So they all cross, 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 cross. Now, you don't need to add the multiplicity. Its degree is x cubed, and it's positive. So you know it goes through 0, it goes through 1, it goes through -8 over here, and you know because of that x cubed, it's rising to the right, falling to the left. So crosses through. I don't know exactly if those humps are right, but that it's a general picture of your graph. Okay, so the thing that we need to be able to do is you're going to be asked a question like this. Okay, and you're like, what in the world does that mean? Okay, end behavior. So like I give you some delta math. Find the end behavior. Well, what is x arrow infinity f of x? What we should know is we know that that stuff means nothing. I need to look at that. It's negative and it's even. Negative even goes down and down. So what does this mean? X going to infinity is looking at the right. X going to negative infinity is looking at the left. Well, look at your two arrows. This is my arrow to the right. It's pointing down. So this means where is my graph going? It's going down. What does down mean? Negative infinity. This is my left arrow. Where's my left arrow going? It's going down. Negative infinity. Okay, so same thing here. If I give you a picture and say fill that in, you need to think this is right, this is left. To the right, where's your arrow going? It's going up. Up is infinity. To the left, where's your arrow going? It's going down. Negative infinity. If you think of when you fill those in, you're going to have either, if they both go up, they're both infinity. If they both go down, they're both negative infinity. One goes up, one goes down, they're going to be different. And it just, x to infinity is right, x to negative infinity is left. So delta math, they ask about maxes and mins. Okay, so that's the last thing that, and you have to realize that when we graph these polynomials, we get more terms. Okay, so it's not just like a quadratic where there's one term. So when I look at this, roots, zeros, x-intercepts, those are all where does it cross the y-axis. You know, I could say x equals -5, x equals 0, x equals 2. Local maxes, those would be high points. Not the arrows. These would be points, like in the vicinity. It's the top of a hill. Like we could call them peaks and valleys. The top of a hill, the bottom of the hill. Local min, low points. You can have more than one. Okay, so when you look at this picture, this is a max. It's a high point. That's a min. That's a low point. That's a max. That's a high point. These are nothing. Those are just going down to infinity. That's actually end behavior. So end behavior, where's my thing going to the left? Negative infinity is left. My arrow's going down. Where's my arrow going to the right? My arrow's going down. So they're both negative infinity. That's sort of, you know, I mean, you look at this, this would have one min, one max. How many x-intercepts or solutions does it have? 3 x-intercepts, 3 solutions. End behavior. This is left, negative infinity. This is right, positive infinity. Where is your arrow to the left going? It's going up. Up is infinity. Where is your arrow to the right going? It's going down. Down is negative infinity. That should sort of, you should be able to do it. But just realize, again, you don't need a picture. If you're using a picture, you're cheating. Okay? I should be able to look at these equations and know where they're going. Negative, odd. Negative, odd is a John Travolta, but if it's negative, it's opposite. Positive, even, both up. Well, how do I fill this in? Where's this arrow to the right? Up. Where's this arrow to the left? Up. Where's this arrow to the right? Down. Where's this arrow to the left? Up. Fill them in. We'll talk about behaviors as we move on. But that should help you with the homework that's given.